Good afternoon, everybody. My name is Bryant Jerome. I'm a student of Dr. Alabastri's, working with a few other groups at Rice in order to optimize the behavior of single-wall carbon nanotubes as a thermal emitter. Now, single-wall carbon nanotubes have a very interesting property in that they have a hyperbolic dispersion relationship, meaning that along one axis, if you look at it, it's actually conductive, whereas if you come at it from any other direction, you'll find that the dielectric constants will indicate it to be dielectric in nature. What this means is that effectively, single-wall carbon nanotubes, once you lay them out in a film, have an infinite photonic density of states. There are an infinite number of ways you can pick on this cone to arrange a given K vector. In that sense, it means that you have a greatly enhanced absorption and, by extension, emissivity in your material when comparing it to conventional isotropic materials, which means that these single-wall carbon nanotubes would be excellent if you place them in a reactor designed to capture waste heat and turn that heat into electricity. So, there are two separate conditions that we've found that will actually result in single-wall carbon nanotubes taking in infrared light and thereby re-emitting it at some later time. The first is exciting surface plasmon polariton pairs, which is a fairly well explained phenomena in metals. And the second is the unique coupling described by the hyperbolic dispersion itself. We go through, calculate both of these values for a given frequency, see what angle we need to put our incident light at through a diffraction grating in order to have these effects show up. And then we go in through console, run some code, and see numerically what we would expect the absorption spectrum of this material to be. A quick note on a lot of the models, we calculate our dielectric constants using a Lorentz fit around the E and Z point, where the E and Z point is just where your parallel component of your dielectric constant will go to 0. Everything past that is just going to be anisotropic, but we're not going to have a hyperbolic dispersion relationship, so we don't pay too much attention to it. But yeah, we use the finite element method to calculate the absorption of this material and take a look at what enhancements we can actually expect to see from this coupling to single-wall carbon nanotubes. We see a large peak in absorption due to ohmic losses in the case of the surface plasmon polaritons excitations, whereas the excitations from the grating coupling tend to be a bit more subtle. We can see that it increases to the left of this coupling frequency here, but it's a rather minor effect. So going forward, what we want to do is to attempt to maximize this grating coupling term as much as possible using the thinnest film of CNT possible. In any case, that's more or less what I've been working on for the past couple of weeks. Email me if you have any questions, and yeah, it's good to be here. I'm excited to see what everyone else's projects think.